In this video, I'd like to talk about the math question of the day for February 24th, 2023. And for this question, we need to find the area between the x-axis and the function f of x when x is between 1 and 7. So to answer a question like this, you might notice that you need calculus, you need integral calculus for this. So at this point, go ahead and pause the video, see if you can work through this on your own. I do recommend drawing a picture of this to get a better idea of what's happening. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, we can start working through this together. And if you do have suggestions for future questions of the day, feel free to leave that as a comment. Now, I do recommend drawing a picture of this just so that you can get a rough idea of what's happening. And we're looking at x values between 1 and 7, so we do need that many tick marks, 2, 3, 4, 5, 6, 7. We'll go one more. And we'll need some y values here as well, just to throw in so that we can actually plot this function here. And notice this is a quadratic function, a parabola, and it's in vertex form. So the vertex of this function is at an x value of 5 and a y value of 2. Notice that when x is 5, this expression goes away and we just get back a y value of 2. So if it's ever in this form, that's how you find the vertex very quickly. If it's some expression squared plus a number, and you could also have some constant out front multiplying. But if it's in that form, just ask yourself which x value makes this squared expression 0. If you plug that in, you'll get back this is your y value, and that's your vertex. So we can plot that point at 5 right here, comma 2. And it's an upward facing parabola since it is a positive coefficient in front. The coefficient is just 1 in this case. If it's negative, then it goes down. So this goes upward, and we could plot some more points if we want. Like if we plug in 1 and 7, 1 would give us negative 4 squared, which is 16, plus 2, which is 18. So at 1, it's fairly high up. And at 7, we get 2 squared, which is 4, plus 2, which is 6. So at 7, we can actually plot that. That is right about here. And we'll get some symmetry. If we go over 2 to the left, we'll get that same y value. And let's just sketch in this curve here. And we need to find the area between the x-axis and the function when x is between 1 and 7. So let's draw some boundaries in here. We know that we're looking at the area between the x-axis and the curve, but we're cutting it off at an x value of 7 and an x value of 1, so it's going to be hard to perfectly visualize this. But essentially, we're finding this area here, which you can imagine is fairly challenging since this is a curvy shape here. And if you haven't taken calculus, you've probably seen how to find the area of squares, rectangles, or circles, or triangles, or simple shapes like that. But curvy shapes become a lot more difficult. And for that, we need to use integral calculus. We need to take an integral of this. And I won't go through all the foundational ideas of what an integral is in this video. You can find that information elsewhere. But essentially what we're doing is splitting up this area into a bunch of rectangles. You can imagine rectangles maybe like this. And you can see those rectangles don't perfectly approximate that area. There is a little gap at the top of those. But when we fill out all these rectangles, we'll have lots of gaps, and it will be an approximate answer. And the way to get it to be an exact answer is to shrink these rectangles, to make them smaller and smaller so that they eventually perfectly approximate the curve. They, in some sense, become a line with a width dx, which is extremely tiny, maybe infinitely small in some sense. So we have this line, and when we draw lines, they will perfectly approximate this curve. So that's a very informal idea of what we're doing here. It's a little bit more complicated than that. We need to be a little bit more careful. But the idea is that we're going to approximate this curvy shape with a bunch of rectangles and then just shrink those rectangles down so that they perfectly approximate it, or that we get an exact answer. And then we have to add up all of those rectangles to find the total area. Now, that sounds complicated because it is a bit complicated. We have to add up an infinite amount of rectangles here, but this reduces to a relatively simple operation where we will take what's known as an integral. This is just an elongated s here. This just means sum. And we have limits of our integral. We start at 1 for our x value and we go to 7. And we're integrating this function f of x. That's this value here. But we're adding up all these rectangles. So we need to find the area of that rectangle. It has a height of f of x. That's just the function value. And its width is this very tiny amount, which we call dx. And we will add up all of these areas of these rectangles between an x value of 1 and an x value of 7 here. And that's what this notation here means. Now, to actually compute the integral is relatively straightforward, but for this function, what I would recommend doing is actually multiplying it out, since we'll want to use the power rule for integration. So we need to multiply out this perfect square here, x minus 5 times by x minus 5, and then we'll add 2. So if we distribute, we get x squared minus 5x minus 5x, so that's minus 10x, and then minus 5 and minus 5, that's plus 25, but then we add 2 more, so we get 27 there. And let me just make a little bit of room so that we can actually compute this integral now. We can rewrite this as the integral from 1 to 7 of f of x, which is this thing. We have x squared minus 10x plus 27, and we multiply all that by dx, just the width of these rectangles. And the power rule for integrals, or integration, works the same way as the power rule for derivatives, but in reverse. Since, remember that with a derivative, when taking the derivative with respect to x of x squared, we bring down the 2, and we decrease the exponent by 1. So the derivative of x squared would be 2x. But we could also go in reverse. When taking the integral of x squared dx, we just need to remember that integrals and derivatives are inverse operations of each other. They essentially cancel each other out, or they go in opposite directions, just like multiplication and division. So when we integrate this, we increase the exponent by 1, but we divide by that new exponent. And this should make sense when we take its derivative. Now, I should be careful. We would have some constant of integration out there, so I'll just put a plus c since we don't have bounds on this. But when we take its derivative and go backwards, we should end up back at x squared, since derivatives and integrals, or antiderivatives, cancel each other out. And when we take its derivative, we bring the 3 down, which cancels the 3 in the denominator, and we subtract 1 from the exponent, and we get back to x squared. So that's the general idea with the power rule. We increase the exponent by 1 and then divide by that new exponent. And you can imagine a constant is really just x to the 0 power. So when actually computing this integral here, we would have x to the 3rd over 3. This becomes minus 10x squared, and then we divide by the new exponent. This becomes 27x to the 1st, since remember this is really times x to the 0, since x to the 0 is just 1. And then we divide by the new exponent, which is 1, so we don't have to do that. And we will evaluate this integral between 1 and 7. So we will plug in 7, compute that, and then we will subtract the value computed at 1. Since remember that the fundamental theorem of calculus, let me use a different color, if this goes from a to b of f of x dx, the fundamental theorem of calculus says that this is equal to the antiderivative of our function f evaluated at b minus the antiderivative of our function f evaluated at a. So we're applying this fundamental theorem now. We found the antiderivative. This is essentially our big F of x. And now we just need to plug in b and a here, or 7 and 1. And we could make a slight simplification since notice that we have 10 over 2. So let's just rewrite this. We have x cubed over 3 minus 5x squared plus 27x. And again, we're evaluating between 1 and 7. So let's start with 7 first. We do 7 to the third power and then divide that by 3. And we get 343 over 3. Then we do 5 times 7 squared. Well, 7 squared is 49, and 5 times 49, or 5 times 50, would be 250. And subtracting 5 from that, we would get 245. So we are subtracting 245. And then lastly, we need to do 7 multiplied by 27, and we get plus 189. We can simplify all that as we go. And then we'll subtract everything evaluated at this lower bound, 1. So we plug that in, we get 1/3 minus 5 times 1 plus 27. So let's go through. We can use a calculator here to simplify everything so that we can ignore this fraction arithmetic. But of course, if you want to do the fraction arithmetic on your own, feel free to do that. And once we simplify everything, let's continue down here. This expression here, this upper expression in parentheses, simplifies to 175 over 3. And then this lower expression right here simplifies to 67 over 3. And carrying out the subtraction, we would get 108 over 3. But 108 is divisible by 3. This is just 36. So what we found is that the area underneath our curve, this parabola here, between x values of 1 and 7, the area under the curve between the x-axis and the function, all of this area here is simply equal to 36. And for these can be a little bit challenging to check, but there are many online calculators that you can use that will actually calculate integrals for you. So I encourage you, use those just to check your answer once you feel relatively confident that you did everything correctly.